pues, ¿qué mal de copia? Que le diga a China que consiga el Nexus 6 que trabaja en Google. Trabajo, ¿cierto? ¿Sí? No lo puede conseguir él. El Nexus 6. Dice que le diga nada. Que lo consiga por
¿Está cargado?
Bájale un poquito.
¿Cómo se le baja? O sea, súbele.
Sí, apágale mejor.
¿Por qué apagárselo?
Hace frío.
Trae abrigo. Trae abrigo. Le metiste.
Hace frío.
Ya mismo.
No me tomé el café. Ya decía yo. Te pongo una mitad. Es bien diferente. Mira, es personal. Sí, es chévere. Muy grabado.
Okay. Welcome back. Okay, what how we treat a real ground profile. The actual ground profile is very different from the very simplified model that we have seen before. Instead, of the height of the profile, we use another parameter, sigma. This is the standard deviation of the profile. Sigma is the standard deviation of the surface irregularity. How do we calculate that? Okay, let's assume that our ground profile is something like that. So we call this x-axis. This is the profile of our ground. This is x1 and x2. And let's assume that this is, on the vertical axis is the, for example, the height above sea level. And let's call this height as a function of x. So as a first step, we calculate the average h, the average height of our profile. L'altitude media. And this is calculated as an average value, that is, this is a continuous function, so this will be 1 divided x2 minus x1 times the integral, as the average value is always defined, integral from x1 to x2 hx dx. And once we have this, we can calculate the standard deviation very simply. We can calculate the variance and then take the square root of the quantity. This is 1 divided by integral from x1 to x2 of h dx. This is nothing but the ordinary definition of variance. The only difference is that in this case the function is our profile of the ground. So if you have a map of the ground, you can easily calculate that quantity. Now, once you have the standard deviation, that is the square root of this thing, the Rayleigh criterion translates to calculate the coefficient C, that is actually the difference phase, like this. You use sigma instead of D. And then you say two criteria. If C is smaller than 0.1, you have a specular, perfectly specular reflection. If C is greater than 10, you have a highly diffused reflection. What is good in highly diffuse reflection? That you can ignore the presence of the reflected wave. You don't care, if you are in a highly diffuse situation, you don't care about the reflected wave because it does not exist. It is so weak that it does not exist. You start worrying about the reflected electromagnetic wave if you are in a specular reflection, and obviously everything in between is a kind of mixed situation. Now, it's surprising if you put in the numbers what you get. Just to give you some feelings. If you work at cellular frequency, 900 megahertz, for example, the wavelength at this is 33 centimeters. So you have very small wavelength, 33 centimeters. If the incident angle C is equal to 1 degree, very, very grazing angle, to have a highly diffused reflection, that is, to neglect the reflected wave, you need a standard deviation sigma quite large, 15 meters. That is quite often, even if your wavelength is so small, 33 centimeters, obstacles, terrain irregularities that are of the order of several meters still give rise to specular reflection if the incident angle is very low. Then depends on the geometry, as usual. See and lambda. Okay, so the idea is if the surface is very rough, you don't care about the reflecting rate. If the surface you have to deal with is smooth enough to give a reflection, a significant specular reflection, then you have to worry about the reflecting factor. They take some countermeasure that we'll see later on. Okay, then we will investigate those things during the exercises. Questions before we move on to the atmosphere? Any questions? I think this is finished. Okay, let's move on to a completely different topic. That is now, the troposphere is that the part of the atmosphere that goes from ground to about, for our purposes, 13 kilometers of height. That's what we call troposphere. There are two important effects in the troposphere. Attenuation due to gases. Depending on the frequency you are working on, you can experience also very strong attenuation due to gases. The good news is the gaseous content is pretty constant. So this attenuation is usually stable in time. Apart from one gas, that is water vapor. Water vapor is highly variable in time and space. But let's say that you usually have this kind of problems, gaseous attenuations, at frequencies above 10 gigahertz. So those are frequencies that are not really of interest for our system. So we can neglect for our studies gaseous attenuation. What is most important are the variations of the refractive index. we will see that refractive index also is highly variable in time and space, because it is related to pressure, temperature, and humidity. Those are very small variations we are talking about. Nevertheless, the small variations have a huge impact on radio wave propagation. The effect, I anticipate what we are going to find later on, the effect is that the electromagnetic wave does not propagate in a straight line, but is bent toward the ground or toward the sky, depending on the status of the atmosphere, and is continually variable. So your electromagnetic wave keeps on wandering around. We see causing a lot of problems, all kinds of problems. Okay. Refractive index. Let me first of all remind you what refractive index is. It is indicated with small m, and it is the square root of the relative dielectric constant. Now, in the atmosphere, this number is 1,0000 something. This something here will cause huge troubles. What is after those 4 or 5 zeros? That is what is causing trouble, that variation here. Okay, since it is almost close to 0, we don't use refractive index. We use a related quantity which is called refractivity. Sounds the same, but it's not the same. It's simply defined, refractivity is indicated as capital N. I hope you can still see this. It's defined as n minus 1, so we can get rid of the unity, and then everything multiplied by 1 million. So we amplify this part here. And the refractivity n has got a very precise relation with the status of the atmosphere. Okay, maybe I use red because this is going bananas. Maybe it's better. Refractivity has got this expression, 77.6 T divided by T plus 3.7 10 times E divided by T squared, where P is the pressure, air pressure, millibar. T is the temperature. Kelvin, absolute temperature. And E is the water vapor pressure. It's something related to humidity. Now, you can imagine that even if you take this room, for example, temperature, humidity, pressure is pretty stable everywhere. But temperature and humidity can be variable from point to point. So really, the refractivity is a scalar field of the space, changes from point to point. Nevertheless, there is a trend, even if there is this fluctuation, there is a trend, a very precise trend with height. Because you know that for increasing height, pressure decreases, temperature decreases, water vapor content decreases. So there are random fluctuations, but there is a trend. So we take this function and we extract two components, the so-called stratified component. This stratified component is obtained by averaging the refractivity over the horizontal plane. That is, you take an horizontal plane and you make an average, and that's what you call stratified component. So in that case, the refractive index will be only a function of z, where obviously this is height h above the ground. And then you have a turbulent component. That is the difference between the real value and the average. It is what is left once you have averaged everything. Now, the turbulent component has an effect, has the effect of reducing the coherence of the wavefront. I will not go into the details because we are not interested in this effect. But to tell you, to let you understand what this effect is, the turbulent component is the responsible when you look, for example, during warm days, you look at distant objects, you see them trembling. This is the effect of the turbulent component. Makes the object look trembling. It's the same on radio waves. The received signal is not exactly stable. It keeps on oscillating, it keeps on variating with very small variation. This is irrelevant for our applications. We are more interested into the stratified component because, as I said, the effect is stronger. Now, let's focus on this. As I said, the pressure, temperature, and water vapor pressure decrease with height with respect to the ground. So if you model this variation, you find out that this is a negative exponential function. Where h1 is a reference value of 7.3 kilometers, roughly, and 0 is the refractive index at sea level, h is the height above sea level. So if we make a graph of this component as a function of height, and you here want to plot n minus 1, you start from a value that is n0, and then exponentially go to 0. We shall see in a bit that the effect of this decreasing refractivity is to bend the electromagnetic ray towards the ground. Obviously, when you are very high above ground, when your height is very high, you are in vacuum. So here, n is equal to 1. Remember please that the refractive index of vacuum is 1, so n minus 1 will be 0. So this difference will be 0. So this is n0 minus 1. This difference will be 0 when you go very high here. Okay, let's see what is the effect of this gradient. Is this negative with this exponential variation, or in general with the variation with height of the refractivity. Let's calculate the so-called radius of curvature of the electromagnetic ray. Okay. In vacuum, as I said, the electromagnetic rays would be propagating along a straight line. I anticipate that on our atmosphere, you launch an electromagnetic ray horizontally and it propagates like this. And what we want to calculate is the radius of curvature of our electromagnetic rays. Please do not confuse this rho with the reflection coefficient of the graph. As I said, unfortunately, keep on using the same letters for different things. This is quite confusing. Okay, so let's call this point here point A and point A first. This is constant surface or plane. The 2 points, point A first, they lay on a constant phase plane because the 2 electromagnetic rays on every surface that is perpendicular to the electromagnetic ray must be constant phase plane. That is, the phase of the electromagnetic wave in this point A must be the same as the phase in point A first. That's why I call them constant phase planes. Now, the same applies for B and B first point. So this is plane 1, and this is constant phase plane 2. Now let's assume that the 2 electromagnetic rays are traveling very close to each other. So we call this delta rho, the distance between the 2. And we call also delta alpha the angle at the vertex of this circle. Now, if those 2 planes are constant phases, then the phase variation when you go from A to B must be the same when you go from A first to B first. 2 electromagnetic rays, they travel different lengths, but since those surfaces must be in constant phase, the phase rotation from A to B must be the same from A first to B first. So if we call delta P1 and delta P2 the phase variations along those trajectories, delta P1 must be equal to delta P2 if the 2 planes are constant phase. But what is the phase rotation when you go from A to B? Is the propagation constant beta times the length of the arc AB. And the phase rotation when you go from A first to B first is the phase constant here that can be different. That's the trick. The reason why the electromagnetic ray bends is that the propagation constant of the atmosphere changes with height because the refractive index is changing. So we have for the secant beta plus delta beta times the length of this arc. What is the length of those arcs? Well, easy is the radius times the angle. So AB is going to be rho times delta alpha. And the first is rho plus delta rho times delta. Okay, so now we put those values into our equation and we get beta rho delta alpha must be equal to beta plus delta beta times rho plus delta rho times delta. And this delta alpha can be cancelled out, and we can further simplify our equation because we get beta rho plus delta beta times rho plus b delta rho delta. As you see that immediately those two cancel. And this one, since reasonably delta rho is much smaller than rho, and delta beta is much smaller than beta because we are talking about small variations. This quantity, that is a product of two very small quantities, can be neglected. It's very small when compared to the other. So we are left with only very simple with those things here, that is delta beta divided delta rho is equal to minus beta divided by rho. And how this links, please remember that we are looking for the radius of curvature. We are trying to calculate this one. Yeah? Don't forget what is our target. How those terms are related to the refractive index? Well, please remember that beta is 2p divided by lambda. That is 2p, lambda is the velocity of the wave divided by the frequency. The velocity of an electromagnetic wave is c divided the square root of epsilon r, if you retrieve the information that we gave the first day. That is c divided by n, the refractive index. So you end up with 2pf divided by c times n. And this is the propagation constant in vacuum where the velocity is the speed of light. So this thing is beta 0 times the refractive index that, as you possibly remember, depends on the height. Please remember that we are launching those electromagnetic rays almost horizontally. So this delta rho is, in practice, equivalent to a delta height. So if the electromagnetic rays are almost horizontal, that distance is the difference in height between the two electromagnets. Please note that rho is not. The variation in rho is the variation in height, but rho is not the height. This is one typical mistake. So, if we put everything into this equation and we solve the thing for rho, we end up with the following equation. Minus m that you obtain, there is one is missing, delta beta is obviously beta 0 delta n. So this equation is minus n divided delta h. If you simplify the beta 0 in that equation. And since n is almost equal to 1, because it's different from 1 at the 5th digit, this is minus 1 divided delta n divided delta h. Or, if we use refractivity, 10 to the power 6 delta n divided by delta h is the gradient derivative variation of the refractivity with height. And now we see what the effect is. Questions so far? Okay, standard atmosphere. Standard atmosphere will be, the concept of standard atmosphere will be clear later, is the average, or better, the median atmosphere. Is representative of a standard situation that never really happens, but it's something that is on average happens. It doesn't never happen because the atmosphere continuously changes. So, in standard atmosphere, if you evaluate gradient delta n divided by delta h is minus 37 kilometer to minus 1. This, if you put this number into that equation, it corresponds to a radius of curvature of 27,000 kilometers. It's not small, but it is important nevertheless. So what happens when you your antenna transmits an electromagnetic ray on the surface of the Earth? Okay, let's assume that this is the surface of the Earth. As I told you yesterday, I think the radius of curvature, if we approximate Earth as a sphere, the radius of the sphere is 6,370 kilometers. And you have your antenna on this place, on top of the Earth. Now, if there was no atmosphere, or if the atmosphere was uniform, you would launch an electromagnetic ray, and it would propagate along a straight line. What happens in our planet for the standard atmosphere is that the electromagnetic ray is bent toward the ground with a radius of curvature much bigger than the radius of the Earth, of 27,000 kilometers. We shall see in a moment that this is the standard atmosphere. That is, this is what happens on average. But in any moment, the electromagnetic ray, we will see, can do anything from going along a straight line, going like that, going like that, or even bending upwards. We shall describe this behavior from a statistical point of view. But before doing that, we have to solve a problem. How do we deal with a bent electromagnetic ray? It is very inconvenient to design a system taking into account bent electromagnetic rays. It is far better, far easier to use straight propagating electromagnetic rays. So what we do to solve this problem is to distort this geometry so that the electromagnetic ray propagates along a straight line. And we see how we do that. Yes.
Would you repeat the message? That was perfect.
When we're talking about the distorted geometry, that one. If you want to make a plan of a radio system, in particular, we will see if you want to calculate the coverage area of a transmitter, it is very unpractical to do that by considering bent electromagnetic waves. If you would like to deal with straight electromagnetic waves, but they are bent in practice. So what we are going to do is we straighten the electromagnetic wave and we distort the geometry of the Earth so that the electromagnetic ray is straight. We correct, in other words, the curvature of the Earth so that then we can plan our system with only straight electromagnetic rays. So, we see the so-called distorted geometry that will lead us to the equivalent Earth rays.